The previous chapter, this chapter and the forward, oh hell yeah. I love this material a lot. So let's cut to the chase here, because now we could start talking about some really cool shit here, finally. So let's, I think we should review briefly before we move on. And ultimately what we did last time is we started talking about relativistic momentum and kinetic energy. In real life, we can't really separate the two. In fact, one of my favorite 4A questions that piss a lot of people off, but I think is a really good one, is this. Can you tell me the difference between kinetic energy and momentum? There's some real subtlety there, but we'll keep moving on for right now. Say that again?
What about inertia? What's the difference between...
Do you mean inertia? You mean inertial mass? That's the way we define mass. It's the same way it's defined in relativity. When we say mass, it's that's the definition. Textbooks kind of, I don't want to drop the F-bomb, but yeah, textbooks screw you up on mass. Yeah, textbooks really piss me off when they talk about mass, but we're not going to talk about mass. We're going to move on here. And so ultimately, we made a couple of statements here. What we saw here is that conservation of momentum and energy continue to be the laws of the land. They have to be. Principle of relativity. The laws of physics are the same for all inertial observers. So you can't just throw them away. So what this means here we needed to expand our view of individual definitions. That means that to keep these guys, we had to redefine things. And what we defined here is we said that the momentum had to be written this way, right? It had to be written this way. And the kinetic energy had to be defined in such a way that it was this way. We had to redefine these to make sure that conservation of momentum and energy had to be the same. And so as a consequence, we look at how do we define these things, right? Remember, if I write a term momentum, it's meaningless. The definition of momentum is only with the impulse momentum theorem, period. Now there's some other ways to look at momentum in a more advanced way, but it's beyond the scope of this course. But ultimately, momentum is defined by the impulse momentum theorem, right? So from the definition of momentum, and what do I mean by that? That the only thing that's meaningful is the change in momentum. And it's this guy, right? So what did relativity show us here? It says this. Imagine that I have some rocket, right? And it's moving with some initial momentum. Now, because of the thrust of this rocket, we know that there's going to be some force. And we could say that the force is constant. But thrust rockets don't have constant forces, right? Those things have some complicated thing here. So you can imagine that you have some rocket, and what you're going to do here is that there's an impulse that's applied to this rocket. That means that over some time, the rocket now is going to be moving at a higher momentum, right? And that's because the thrust continues to act on the rocket. And so when I look at the impulse, what does it actually say? If this happens over some time element, right? We integrate that over some time element. Then what this tells us is it says this, that how do I say this? By applying, so to apply an impulse such that U approaches C would require an infinite impulse to change the momentum. So in other words, if I take the limit as U approaches C of this impulse, then we find here that this approaches infinity. And as we already know, it's impossible to apply an infinite impulse, which then implies what? No object can go C. That's what the impulse momentum tells us. That's the easiest way, or one of ways, to state that no object can go the speed of light. But you know, we don't have to just talk about momentum. We can also say the exact same thing from the work energy term. We can also state the exact thing via the work energy theorem. And so it's the exact same picture, but this time I have kinetic energy. And this time I'm going to increase the kinetic energy. So if I start to increase the kinetic energy over the situation here, instead of thinking about this in terms of instead of time, I'm now going to do this over what? Some distance delta x. And what we see here, that according to the limit as U goes to C of what? The integral, oh man, I forgot to put time up here. This would be the force times dx this time. And if you do that, you also get an infinite amount of work that you have to do. So here, we say that that it's impossible to apply, not to do infinite amount of work. So you conclude from the same thing that no object can go C. No massive object can go C. So it doesn't matter how you look at this thing, it's still the same type of thing, that it requires an infinite amount of work or infinite impulse to change the momentum or to change the kinetic energy of an object. So that's the only way relativity tells you that massive objects cannot approach the speed of light. So then what we started to do here is we started to interpret this thing here. And what we did here, we started to ask, so what is the new kinetic energy in relativity? And this is what we found.
Hey, Carlos,
Yes.
I have one question to start up. So if massive objects can't travel at sea, how fast can it actually go? Like how close can we get?
Well, that surely is not a soup question, because you need more details than that. And what I mean by that is that, like electrons, you can get pretty damn close to C in a very short distance. But if you take like a gold atom, which we'll talk about today in example 1, they can't get to the same gamma factor. And so the rest mass of a particle really tells you that that the energy can go up pretty high. But at this, we really got to go more into the details to really explain that. We have to say it individually, if I could say that. Okay.
Yeah, I get it.
Yeah, but you'll see. I'll give you an example right now, which I think is super cool. One, it involves QCD, which is a big passion of mine. No, I'm a has-been. Many years ago, it was a passion. Now I'm just a pedestrian. But there's some really cool stuff. And hopefully we'll get to it here real soon. So moving on this thing here, what I'm going to say here is that what we found here is that when we did this work, we calculated this work which caused a change in kinetic energy. What we found here is that we got a term that looked like this. And what's interesting here is that this guy, of course, is kinetic energy. And we were trying to decide what were these guys right here. And one of the things that we could interpret here is that if I write this, then I can have a term that looks like that. And if this is the kinetic energy here, then the interpretation here is that this must be some type of potential energy. And it turns out that then this implies here that this guy must be the total energy. So by doing this, we ended up then starting to reinterpret what is really going on. By the way, this equation right here is one of the worst equations in relativity. So huge red flag. I don't really want to write this because it's, sometimes it's useful, but it's more from a conceptual viewpoint. But almost never, ever, ever use this equations for calculation, because once you start trying to use this, you're going to go into an alley that you can't turn around from. You're just going to go into a dead end. I promise you, I promise you, I promise you, not the way to go. I'll be very specific how you should approach this. And it's kind of funny because on the very first example, I'm going to use this relationship. Why? It's just because the question's in the right form. It just doesn't happen that way in reality. But remember, this is only useful conceptually. So now what we want to do is we really want to interpret what this new potential energy is. So there's a new form of energy. And this is called the rest energy. And really, what people typically talk about this is the equivalence of mass and energy. And let's go look at that. So what you're going to find here is that the master himself gave I think one of the best interpretation of this equivalence of mass and energy. What is this new energy? And this is Einstein's thought experiment. He is so good at these thought experiments. It's like scary, actually. The dude, I swear, he has an alien mind, because I can't comprehend how he gets to some of the things that he gets to. But this is a beauty right here. So check it out. Here's his thought experiment. What he does here is he's got a box. So let's say that this box is this length. Okay, and inside this box, he has an emitter. So this guy's a light emitter, okay? And then over here, there's a detector. And so what do we know about this thing here? Well, according to this thing here, oh, by the way, I assume that you know that when you say total momentum of a system, you're talking about conservation of center of mass. That's a big deal. And I'm assuming that you got that in 4A. So now that we all agree that you got that in 4A, we could move on. So what we want to do here is we want to do the following thing here, is that I'll start with the series of points here. So the first point I want to say here is that there are no external forces acting on box. Okay? If there's no internal forces, then this means here that the momentum of the system is conserved. And the reason why I can say that here, right? Because this means here that if this external force is the derivative of the system of the momentum, and if there's no external force, then that means that the momentum of the system must be the same before and afterwards. But wait a minute. Momentum of a system, what it implies here is that the center of mass location is conserved. That means before the interaction and after the interaction, the center of mass is fixed. So this means that before and after the interaction, center of mass location is fixed. That's what the total momentum of the system implies. So that means here I go. That center of mass cannot change, no matter what. So then what happens here? So the next thing that happens here is that the photons are emitted, or light is emitted. Okay, so then the next piece here is that we're going to say here is that, here, let me change this guy. So what we're saying here is that, oh, come on. So what we're going to say here is that light carries momentum and energy. And how do I know that? Well, you get a sunburn. How do you get a sunburn? They have to carry momentum and energy to go from the sun to your skin. So they have to. And so what we could say here is that because and because of momentum, the light packages or packets, what I mean by light packets, so you could imagine that you have something. Do I know what light looks like? Nope. Does anybody know what it looks like? Nope. These guys are carrying some type of momentum, right? And typically the way we call light is we use a gamma factor for light. So light is carrying momentum. So these guys then are shooting. And what we know about this is that we know light is massless. So here we go. So now what's going to happen? So now the detector's doing what? It's shooting these light particles, these packets. And as they shoot them, what's going to happen here is that they're carrying momentum to the right. Okay? So that means these guys in here, they carry but wait a minute. If the momentum initially is equal to the momentum finally, and it's zero because nothing has been shot yet, then that means that the center of mass is fixed. But if momentum is going to the right, then the box must go to the left to conserve the center of mass location. So then I could come over here and I could say here, so to conserve momentum, light going left implies box goes right. So that means the box has to shift. So then I come in with my box here and I'm going to say, well, that means that the box had to move. In this case, the box had to move what? 1 square. So I still have my objects where I have my source and my detector here, but you could see that it has shifted in order to conserve momentum here. So what I can say then is that I could say the following thing here, is that the box is classical. And what I mean by classical here is that it's not moving with beta, with a large beta. So that implies that the momentum of the box must be the mass times the velocity of the box. Right? In both cases, you know what? Let me be careful. I'm going to write this a little bit better. So it's got to be the mass of the box times the velocity of the box. It's got to be classical momentum. So my question is, what does this all mean? Well, if I want to interpret what's going on here, what we could see here is that, you know what, I should come over here. Well, we know that the momentum before, right, so the initial momentum,
Carlos?
has to be 0, yeah.
Before this, you were talking about how nothing no mass can go to C,
Mhm.
but light has momentum, but it's massless.
Yeah.
So that is tripping me up. I thought we kind of said that nothing can go to the speed of C, but
Yeah, unless it's a massless particle.
hmm.
And you know what? That's part of a discussion of hopefully a little bit later today. And I will discuss that, okay? Now by the way, it's also one of your homework problems. How can light, which is massless, have momentum and energy? Okay. So what does this all mean here? Well, if the initial momentum is 0 and the final momentum must be true, if I pick this to be the positive direction and that to be the negative, then that means that the momentum of the photons minus the momentum of the box must also sum to 0. So what this is telling me here is that the momentum of the box and the momentum of the photons must be equal and opposite. So what does this mean here? So what we could imagine here is that we could imagine the following thing. So we imagine the light is transporting momentum, right? Not transporting momentum, transporting mass, right? It's transporting mass because remember, the total momentum of the system is fixed. And what's associated with the total momentum is the center of mass. So if mass goes to the right, there has to be something going to the left. So it's transporting mass to the right side. However, light is massless, right? If light is massless, then the only way this can be true is if mass and energy are on an equal footing. And therefore, this is what's known as the mass energy equivalence. And it was Einstein's thought experiment. It was this little experiment that he wrote up E equals mc squared. But let me tell you, there's a lot to unpack here. There's a lot to unpack. But that was Einstein's little thought experiment that led to the relationship of energy mass equivalence. And so what's really, really wild about this thing, so this is his intuition, right? So I think this is like super, super deep right here. So Einstein goes and he does this little thought experiment in his head. And he's saying to himself, I know that this must be true because I'm dealing with massless particles. So what does he do now? He then goes and he does Lorentz transformations on energy and momentum. And what pops out? Well, this relationship that they call E equals mc squared. Even though most people don't realize that E equals mc squared is meaningless, has no meaning at all. But I think that's really, really cool that he starts from this physical picture first, and then he moves forward. So to trust his intuition, what does Einstein do? Einstein then uses a Lorentz boost on energy and momentum that links mass and energy together, just like it links space and time. So nobody realized that energy and mass were connected in this way. Just like nobody realized that there was a connection between space and time, as we saw in special relativity when we're looking at the Lorentz boost in those cases. So when he does that, there's a second equivalence. Just like there's an equivalence of space and time in space-time diagrams, there's an equivalence to mass and energy, which is really wild here. Okay, I think that's really deep. So by looking at this, it reaffirms that he's moving in the right direction. So what we want to do here is that we got to sort of like, let's interpret what mass, energy, equivalence means. Okay, we want to interpret this so that it's real clear where we're headed. So what E equals mc squared, this is called the rest mass. By itself, it's meaningless. Okay? Let's be real careful, right? By itself, it's meaningless. So what this is really, so if I look at this thing and ask the question, what does this physically mean? There's a lot of expressions that people use, and I like some of these. It essentially says that a piece of matter has energy of just being, right? And what I mean by that, it has, or maybe I should say, it has its own energy. Sort of like the natural resonance of a system. It has its own natural frequency. Objects of mass have their own. So it takes energy to make mass, and if I make energy disappear, if I make mass disappear, it releases the equivalent amount of energy. But the important piece here that I want to look at is I want to look at an analogy. And this is one of my favorite analogies here. So you could imagine that you have a boulder up here. Okay, so I have my boulder up here. And what we know that this boulder has here, I know that a boulder stores potential energy because it's up on this hill. And how we access this thing, it depends on whether we can get this guy to come all the way down. So if I have a stationary particle in a very analogous way here, you could imagine that I have this particle here. And what we can say here is that in a very analogous way, the particle stores rest energy just by being this particle. And so what we say then is that the mass of a particle is how do I say that? Is a measure of its energy content. In other words, the energy in that boulder depends on what? Not only the height, but its weight. This particle at rest stores this rest energy, and it's only a measure of its energy content when we talk about the mass here. So let's keep going on here. So one of the things here that we should keep interpreting here is that remember that C is huge, right? 3 times 10 to the 8 meters per second squared. So this tells me here that the rest energy, which is mc squared, contains a lot of energy. So if I write m times c squared, then the energy involved here is huge. It's a huge number, right? So this guy is a huge number. So a small amount of mass can put out a huge amount of energy because of that c squared here. So in other words, a small amount of mass contains a lot of energy. And one example that we could think about here is we could think about nuclear explosions. Now, when you look at a nuclear explosion, I should be very, very, very careful now. A nuclear explosion is really it's a release of electrical energy. And what you do here is that you're essentially looking at the high kinetic energy of the particles as they repel each other in the explosion. But where do the particles get their kinetic energy from? They get their kinetic energy by converting some of the nuclear mass into kinetic energy. So for example here, if I have a nuclear explosion, what I'm seeing here, right? So this is my nuclear explosion. That means here that I'm getting all these particles moving away, and these guys are moving away with, with high kinetic energy. So where did these guys get high kinetic energy? So what you find here is that inside the nucleus, a small amount of mass is converted from mass potential. What do we call mass potential? The rest mass into kinetic energy of you know, I guess expanding particles. What do I mean, the expanding particles? It's the particles moving away from the explosion. But you have to do that. So what you're seeing here is that you're not completely, you're not getting annihilation of the nuclei. You're just literally turning a tiny, tiny, tiny bit of nuclear matter into mass potential inside the nucleus. That in turn gets converted into kinetic energy. So that's what I mean. A small amount of mass contains a lot of energy. You know what's really funny? I remember in the early 60s, I used to, movies would come out and people would say, oh, E equals mc squared is responsible for nuclear, nuclear bombs. Well, that's a bunch of hogwash, right? I mean, it's sort of like saying, like, the people who invented computers, oh, they're responsible for people getting hacked, and therefore they should be liable for that, right? That's hogwash. It's how you use the technology that's important. So I think this is what we call what? A capital B and an S here. Bachelor's of Science, of course. But what we find here is that another thing that we should talk about here is that we should talk about that E equals mc squared applies to all energy transformations. Right? It applies to all energy transformations. That means if a chemical reaction occurs, E equals mc squared is there. If I'm talking about, like, what I mean by chemical, I'm talking about like gasoline or coal plants or something like that. Or what about if you're going through metabolizing food, it's there. Or nuclear reactions, it's there, right? I could just keep going on. Any type of energy transformation involves E equals mc squared. So the question is it a big part of the process or is it a small part of the process? It depends on the interaction that you do here. So what this means here is that, as an example, now I'm really nervous about saying this because I'm afraid that you're going to use it out of context. Okay? So let me see if I can not screw this thing up and get you to mislead about what's going on here. So example, let's say that you do work to stretch a rubber band. Well, what we mean by this is that if I do work, then I'm going to change the energy of the system. And I could change the energy of the system two ways. I could change the potential energy, or I can change the kinetic energy, depending on how I'm looking at this thing. But wait a minute. This implies then that there's an energy content increase. So if I take the rubber band and I stretch it and then I hold it, there's an increase in energy content for that period of time. So according to the mass equivalence, we could say here that the rubber band is now ever so slightly more massive. So that's a really, really difficult thing to actually comprehend. What do I mean by that? Well, if the energy content increase, of course it, right? So I can imagine that here's a system. Okay, so imagine that this is my system. So what am I going to do here? What I'm going to do here is that I'm going to add energy. Via work. In other words, I increase the energy of that system. So some people will say, well, this thing is not going to be heavier. But here's a problem. How do you separate kinetic energy from potential energy in a system? So if you're looking at the rubber band, how do you know the amount of energy that you're stretching the bonds of the atoms versus increasing the kinetic energy of the atoms? And so I agree that you can say that if you could truly put it all into potential energy, then according to E equals mc squared, you would see an effective energy content reading that's higher. So by reading its energy content, we then surmise that there must be a higher mass energy content. But I can't sort of like separate the two. They're attached. So does that mean that the particles all of a sudden weigh heavier because, I put more energy into that? The answer is no. It's the energy content that increased. And then we could call it that the mass energy content, the mass potential energy term has also increased as a result. So this word is very, very, very slippery. And you'll see textbooks just literally come out and just say, oh, the mass of this thing is heavier. What do you mean by that? Does that mean that the particles got more massive or that its energy content got higher? You gotta be really careful. I can't separate mass and the speed of light squared. They're one and the same. They're in the same equation, and that becomes slippery here. But here's a very, very clear example. Okay, the best example that I could give you is what happens in particle accelerators. So the question, now I want to look at a particle accelerator example. Now, I don't know how much you know about this stuff, so I'm just going to assume that you don't know anything. And what happens here is that where you see the best example of mass and energy equivalence is literally in particle accelerators. And so what happens here, and the example that we're talking about, we want to talk about matter versus antimatter. Now, the only thing that we know here is that people have characteristics. For example, Jason has longer hair, he's got facial hair. I've never seen him with eyeglasses, and I don't know how tall he is. Ollie, she doesn't have facial hair, she has shorter hair, and she's not as tall as Jason, right? People have physical characteristics. Well, what we call physical characteristics of particles are called quantum numbers. So the only way you can describe an object in the particle world is that you need quantum numbers, and they give you very distinct details. And so what you'll find here is that I'm going to give you a white lie. Matter has positive quantum numbers. So remember, what I'm telling you here is a lie. But we'll probably never see it in this course, maybe at the very end. Actually, when we talk about Schrödinger's equation, we'll talk about this. So there's this thing called antimatter. So antimatter exists. And what's special about antimatter? Well, instead of positive quantities, it has negative quantum numbers. So here's the thing. If equal amounts of matter, antimatter, are combined, then the sum of quantum numbers equals 0. But wait a minute, a particle has characteristic quantum numbers. Antimatter has characteristic quantum numbers. So if something sums to 0, then that means that you get no particles. And sometimes people call, oh, it's just radiant energy. I mean, I don't know what you call this stuff, but it just means that there's nothing that exists there. So according to conservation of energy, you cannot get rid of that energy. So it goes into this. So what happens in a particle collision here? So what happens in a particle collision is that you have two particles. Let's say one is red, one is blue. They're both moving towards each other. So here I got matter, here I got antimatter. And so what happens is that if this is the before, when these guys actually collide here, you literally get a region of high energy density. Okay, so that means in this area here, you get this high energy density region. And so what you get here in this pure energy state here is that you can, if you completely annihilate it, what you're doing here is that you're converting kinetic plus potential into something for a brief moment that has no kinetic energy. It has all potential energy. So if I was to sort of like draw a bar diagram, hey Manuel, here's a bar diagram for you, baby, right? So what you find here is that this tells you that this is all the total energy of the system. And what do I mean by total energy of the system? That means that these particles had what? Well, I can't violate energy, right? The principle of energy says it's got to be the same. So what happens is that each of these particles have a certain amount of kinetic energy that's coming in. So when I look at the energy, I'm going to have some amount of kinetic energy. But each of these particles have what? They also have rest energy, right? They also have rest energy. So that means I'm going to have a little bit of energy here. It's going to be in the form of mc squared. But if I truly turn it into radiant energy right here, which means that I'm converting it all into mass energy, then all of this energy here must be in the form of big MC squared. I've converted all of that energy into mass. And this is a big deal for particle accelerators. There's a lot of depth here. So let me explain, what do I mean by this? So to show you what I mean by this, I'm going to give you a silly example. Okay, a silly example. And here's what you find here. This is what I call my watch analogy. And I think I gave this like 30 years ago in a talk. So note that part of this is just kind of a silly joke, right? Geeks don't make cool jokes, they make silly ones. And then we laugh at them because we think they're funny. This is one of them. So in classical physics, if you throw two watches at each other, what happens? You get a shitload of little pieces after the collision, right? You get all this stuff all over the place because classical watches, they don't really interact. They just sort of like, they bust into little pieces here. However, in quantum physics, what happens? I can throw a matter and antimatter watch, right? One can throw matter and antimatter watches. And so what I mean by that is that you could imagine that here's a watch. Okay, and this is going to be my matter watch, right? And it has certain quantum numbers. And I'm going to be throwing it in this direction here. And then I can throw my antimatter watch. So I'm assuming that the antimatter watch rotates in the opposite direction. Right, and as I do that, what I'm seeing here is that in this case here, we know from our previous discussion here that if I can combine equal amounts of matter and antimatter, I get annihilation because I get the complete cancellation of the quantum numbers, which means that for a brief moment, there is no particle in that energy region right there. And so remember what I just said right here. You can get huge mass particles out of this thing. Enormous. Yeah, go ahead.
When you talk about these quantum, I'm not sure about that term, like quantum bursts. Does that go into like this subatomical particle?
Oh yeah, absolutely. Yeah, it's just, I'm not really trying to go into that detail. I'm just saying that particles are characterized by their quantum numbers.
Oh, okay.
Just that's it.
Okay.
And if I don't have any quantum numbers, there's no particle.
Okay.
So if I throw these watches fast enough, what you'll find here is that I can get an annihilation to occur. And these little tiny quantum watches, which are tiny, can produce massive, huge clocks. And one of the biggest clocks that I've ever seen is the Big Ben clock in England. And that thing is huge. That thing, I think it's, I don't know, it's like 40 feet roughly at the base of the square. And the clock itself is like, I don't know, like about 25 feet in diameter. It's huge. In other words, by colliding these particles, you could get things that have very little mass, right? If you look up here, they have very little mass. But I can take part of that kinetic energy and part of that little tiny mass, and I can convert into huge amounts of mass potential energy. My point here is that I can't really separate the mass potential energy from the kinetic energy of the system. They're intermixed. Only in extreme situations do I start to see sort of like, oh, this thing's roughly at rest, so a lot of it is in this mass potential energy. And what we find here is that in particle physics, what we call these guys is we call these guys resonant mass states because they only last a tiny amount of time. But that's what I mean by, this is what happens in real life. So when you talk about a particle accelerator, let me give you an example. At SLAC, you could take a little tiny electron and shoot them at each other. So you can get these guys, okay? And these little tiny electrons, they have a mass energy of 0.511 times 10 to the 6 eV. And I'll talk about these energies in a little bit. And so what we find here is that they can produce a particle called a Z boson. And a Z boson, so this thing here is this massive Z boson. So they can produce a Z boson. When you look at the mass of a Z boson, it's actually about 100 times 10 to the 9 eV. And so I can write this as 100 GeV, and giga stands for 10 to the 9, and then this guy can be 0.511 times 10 to the negative 3 GeV. So if I look at the mass of the Z boson to the mass of the electron, you're going to get essentially 100 times 0.5 times 10 to the negative 3. This guy's going to be bigger by, it's more massive by 200,000 times. So these little tiny electrons can produce something when they collide that's 200,000 times more massive. And when we say massive, we don't mean like we put it on a weight scale, is that its energy content is differ by 200,000 times. That's how I can take two quantum watches and produce like a Big Ben clock. It's a really radical thing here.
Hey, Carlos.
Yo,
Wouldn't you, in this case, then say that mass isn't an invariant? Because it seems like we're adding up masses and we're getting something bigger. And we've talked before about how mass is an invariant. wouldn't this kind of break that
Oh,
down?
baby, no. Okay, I can't talk about that right now. Give me a little bit more time. But I'm not, yeah, no, that's not true at all. But I'll come back and I'll say something in a minute, Nico. No, there's no way.
Okay.
Yeah, but I'll get to the, God, I gotta get moving. I gotta stop talking too much. Here, so let's see if I can go right to where you're at right now, Nico, so we can answer that question. So here I go.
Cool.
So what I want to talk about is I want to talk about conservation of energy and 2 useful energy results. Okay. So here we go. Conservation of energy. So when I talk about conservation of energy, what it means here is that the initial must equal the final. And some people would say, oh yeah, dude, I can go use this guy right here. And I'm telling you, don't do it. Stay away from the light. Don't do it. This is the worst possible energy. If you're going to do a calculation, never, ever, ever, ever use this thing. Ever. Okay? Never, ever use this thing. Bad. It's a bad choice to use it. Okay? So here we go. So for problem solving, here are 2 important relationships. So the first one here is that you can measure the speed of a particle. And this is useful in numerous cases. And the way you can measure it is that you look at the ratio of momentum to energy. So if I look at the relationship between momentum and energy, we wrote this as gamma mv divided by gamma mc squared. And so what happens is that you end up with the relationship v over c squared. So in other words, see that c squared? I'm going to take one of the c's to the other side here. So you're going to get pc over e is equal to v over c, which is beta. This is a powerful relationship. This is a very useful relationship. Let's look at the second one. The second one involves a lot of algebra, which I won't do, but are in my lecture notes. So the second one says, so the most important energy momentum relationship is called the 4 energy expression. Some people call it the 4 momentum expression. Okay? And so when the way you get this is it goes like this. Okay, wait, let me make sure. I got to say this loud and clear. This is only, damn it, for a single particle. Do not apply that to the whole system yet. I'll show you how to do it for a whole system later, but for right now, you treat it for a single particle. And you start off like this here. So you take E total and you square it. And when you do that, you're going to square gamma mc squared squared. And what you're going to find here is that this relationship in the end reads like this. It's going to read 1 minus v squared c squared divided into m squared c to the fourth. And then you get a lot of algebra right here. A lot of algebra. And after a lot of algebra, you get this beautiful relationship. And it reads e squared is going to equal to pc squared plus mc squared squared. This is the four energy relationship. And it's also known as the four momentum relationship. Okay? This is powerful. And this relationship is so deep. There's so much here. Okay? So much here. Okay. I was going to try to wait for this later, but since Nico started it, let's go for it. Here we go. So, remember, mass is an invariant. That's what I told you. Now, let me give you an analogy first, and then I'll go for it. So my analogy here is that if you look at the total energy, it's kinetic plus potential. And I'm going to ask you two questions here. So, is kinetic energy conserved? No. Is potential energy conserved? The answer is no. But energy equal to K plus U is conserved in all interactions. Now let's go this way. So now if I take the four energy, okay, starting with E squared equals to P squared C squared plus MC C fourth, I can rewrite this. And if I look at this thing here, what you find here is that I can rewrite this like this. Okay? If you look at the Lorentz transformations, this is what I'll call the S-frame. If I now do a boost into a new frame of reference, where this is the S prime frame, or any other frame you want to choose, as long as they're inertial frames of reference, this is always a constant. So the Lorentz invariant for mass is that E squared minus P squared C squared. That is the same for all observers, telling you that this is then a Lorentz invariant. So if you were to go back to the clocks and it looks like the mass is changing, if I change the mass, the mass is always the same. It's the energy content. Let me be careful. It's the energy of the system and the momentum system that always offsets each other. So if I was to look at a diagram like this, So if I look at this in terms of a bar diagram, then that means that this guy here is the mass for all observers. And this guy has to be a constant. So since these square terms have to be positive, it means this. That means I can have a system. I think I made this too big, so I'm going to erase this a little bit to make it smaller because I'm going to need the space. Let's say that it's only 2 squares. And I got to move this down a little bit. So if I was to give you like a physical analogy, that represents that. So what that means here is it means this. If I have energy that's going to be, let's say, this amount here. Wow, then this is going to be the energy squared term. Then that momentum in this situation must do what? It must offset this thing so that it looks like this by the other observer. So that I always have that amount. But let's say that a different observer measures a different energy content. And the example that I'm kind of thinking about is that I'm thinking about this. I'm going to move up for a brief moment. I'm thinking about the 2 watches, since that's where it came up. I look at the watch, frame of reference, the center of mass frame, and that's what I'm seeing. And then I go to the Big Ben clock. Well, if I start to look at this scenario here, then that means in this other scenario, maybe the energy has a higher energy content. But if the higher energy content is there, then that means the momentum content must be bigger as well. So if this is 1, 2, 3, 4, then that means the momentum must go down to 4 squares. But the difference always gives you the same MC C4 squared term. It's always a constant. It never changes. That's what it means to be a Lorentz invariant. So when I'm thinking about this, I'm going to call that my prime frame so that I can differentiate between the 2. Oh man, I just got to the best part. Shit. Dude, this is the best part right now. I'll have to wait till Wednesday.
A nice
Give it a
cliffhanger.
teaser.
Say it again?
Give it a teaser.
Oh, dude, the definition of matter and antimatter right now. We need quantum physics, but it was first predicted with relativity, right? Because if you look at this thing here, check this out. If you have E squared equals M squared.
Share your screen, Carlos.
You're not
There.
sure.
Oh, man, God damn it. Right, where are we at? Yeah, but if you're here, right, look, if you want the energy, you got to have the plus and minus. So there are positive and negative energy states. And so you're going to love this. So what does the plus mean? Plus means that you have a particle. So matter is a particle moving forward in space or space-time. Dude, you ready for this?
Yeah.
You have a particle doing what? Moving backwards in time.
No.
Yes, baby. It's moving backwards in time. Or you reinterpret it, or it's an antiparticle moving forwards in time. Dude, is that not deep? Shit, I gotta get my ass out of here. I'll see you guys later. I gotta go to 4A.
Take
See
care.
you later, man.
Bye, Carlos.
All right, later on.
Carlos.